Hello everyone, this will be the first video that I'll be making, and this video is on binding energy. My name is Mr. Palladium, and I'll be guiding you through chemistry, and I'll give a few more lectures, a few more videos soon. So this is my first video, and I hope that you guys like it. So we're just going to start off with the fundamentals of binding energy. For this first video, I'm just going to assume that you've taken like a basic course in high school chemistry. So in basic science, we all know about the atom, about like how people made different models of it, from J.J. Thomson to Bohr and more groundbreaking minds. However, ever since 1932, we all know that we have three distinct subatomic particles that make up an atom: protons, neutrons, and electrons. Now, electrons are involved in actual bonding of atoms to form molecules, and what the role of protons and neutrons are is that they're in a small, densely positive center, which is, of course, the nucleus. Now, these two subatomic particles contribute most of the mass of an atom, as you've learned in basic science. And while the electron does have some mass, it's pretty much negligible. So this mass is represented in atomic mass units, or AMU for short, and 1 AMU is equal to 1 divided by Avogadro's number. Remember, Avogadro's number is the number of atoms or molecules in 1 mole of that atom or molecule. So it's equal to 1 over Avogadro number grams. So that's something that you'll need to know, especially if you want to get into binding energy. So we're going to go into binding energy. So before we start this, remember that elements have these isotopes. And isotopes, since protons define what an element is, the element's identity per se, isotopes have the same number of protons, but they have a different number of neutrons. Take, for example, protium, which only has 1 proton, and deuterium, which also has 1 proton, but 1 neutron. And these are isotopes of hydrogen, since hydrogen has only 1 proton. Now, each of these nuclei have an atomic mass, and you can find out that if you subtract the mass of every single proton and neutron from the mass of the nucleus, you get some quote-unquote missing mass. And we can use E equals mc squared. Now, what this equation states is that the energy in joules is equal to the kilograms that you're observing times the speed of light squared. And we can convert this missing mass into energy to hold the nucleus together. This is known as the binding energy. Or in other words, the binding energy is the energy that's required if you want to convert a nucleus into its individual protons and neutrons. So that's the basic concept of binding energy. So I'm going to bring up like a more easy example for you guys to understand. So imagine that we have like a rocket, okay? Now this rocket's made up of 3 parts. I'll have to import these parts in. I'm just going to arbitrarily name them triangle, square, or rectangle. And star. So currently we have this rocket made up of these 3 parts. Now, of course, the rocket can have more parts. So this rocket can have a mass of, I don't know, let's say like 50 kilograms. It's a simple model rocket that you use for a school project. Now, what we'll do is we'll just simply subtract the mass of this triangle, the mass of that rectangle, and of course the mass of that star. So let me insert a few things in here real quick. And let me give them all like arbitrary rates. So this will be like 20 kilograms. This will be like 10 kilograms. And this will also be 10 kilograms. So what will happen is once you do this, you'll get 10 kilograms of missing mass. And using E equals mc squared, we can convert this 10 kilograms into joules. And this joules is basically like the binding energy, like quote unquote binding energy, needed to hold this model rocket together. So that's a practical example if you want to know that. So right here, I actually got a useful graph for you. This is a graph that models the binding energy of a nucleus. And it's a 3D graph because I made the binding energy dependent on two parameters. The number of protons in the nucleus, denoted by Z, and the number of neutrons in the nucleus, denoted by N. So you can see right here, we have a really steep increase, so maybe a few staggers, and then we have like a gradual decrease. Like you can see the slope kind of just goes down super smoothly. And you can see all these same colored bands just represent the same element. And I'll get to that in a second. So you can see that the graph actually peaks around iron. And that means that the iron nucleus has the greatest binding energy, meaning that it's the most tightly held together nucleus in all of the periodic table. Now, in addition to this, you can see if we're looking at from this perspective, you can see we have our peak, and then it immediately goes down. And what we can do is we can calculate the neutron to proton ratio. And what we do when we find that out is that generally, if you want to achieve the highest binding energy for a nucleus, the neutron to proton ratio, assuming you're like after this point, like maybe after the second period of the periodic table, the neutron proton ratio must be between 1 and 1.5. And this is actually a really well held up fact. You can go check this out online, but generally nuclei who have this ratio are extremely stable. So that's something you need to know. And always, if you end up liking these videos, make sure to subscribe, and I'll see you next time.